Okay, so today I'm going to prove that if we have a measure on R that takes only rational values and the measure of the whole space is 1, then that measure can only take finitely many values. Um, finitely many values belonging to this domain or codomain. And so to prove this, I'm going to start by assuming the opposite. So suppose, for sake of contradiction, that mu takes infinitely many values. Now, I'm going to draw the real line, and I'm going to project it onto a circle here, which is just a cross-section of the Riemann sphere, if you've seen that for the complex plane. So here's my 0, here's my infinity, plus or minus. And this is my real line. And essentially, I'm going to claim that little lemma here, there exists a partition f sub n of R. So if you don't remember what a partition is, it's a family of disjoint sets that cover the space, okay? And so I claim that there's this partition such that the measure of each of the sets in the partition is some rational number which is greater than 0 for all n, okay? And the way I can construct this is I can start with just my whole real line here. And then I can essentially start continuously contracting this interval along this circle, like so, until the measure of my set jumps down from 1, right? And it will do so at some point because this is a continuous deformation and the measure of a point set has to be 0 and the measure of the whole real line has to be 1, okay? And so because of this fact, I know that the measure takes infinitely many values, so it's going to jump down as I continuously deform this interval. It's going to jump down at least accountably infinite many number of times, and each time it jumps down, immediately I can take the difference of the initial and the final sets, and the difference. Let me show you what the difference looks like. Let's say it jumps down from this point to this point, it undergoes a shift, a decrease in total measure. Then I can take the difference in these two sets, and it has to have some non-zero rational measure. And I can do this a countably infinite number of times because of the fact that mu takes infinitely many values. Okay. So that's the basic idea of how I'd construct this partition. And now we know that the measure of R is just the measure of the union of all the sets in this partition. And by countable additivity of measure, we know this is equal to the summation of the measures of each of the sets f sub n. And so we get this summation of rational numbers that has to sum to 1, okay? Because remember, the measure of our whole space is 1. All right. And now the goal is to be able to find a subsequence q sub n sub k such that the summation of q sub n sub k's of the subsequence is irrational, okay? And if we can do that, then I'm essentially going to find the f sub n sub k's associated with those rational numbers, take their union, and then the measure of their union will have to be irrational, which is our contradiction. Okay, so let's prove this. And it's a really beautiful kind of proof. And the idea is that, okay, we have a summation of q sub of rational numbers that converges to 1. So we know that the limit of these rational numbers has to go to 0. And now take the base 2 decimal expansion Sorry, it's late at night right now. Okay, expansion of the summation from k equals 1 to n of q sub n sub k. So say I start with some partial sum of rational numbers. Doesn't really matter what I choose. I could randomly throw a dart on the sequence and just choose whatever I wanted to start off with. Doesn't matter. Okay. And now this is going to equal some 0.001 dot 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 dot. And then essentially we know that this is a rational number. This sum has to be rational. And so this sum has to have must be periodic in its base 2 decimal expansion. Okay, so since it has a periodic base 2 decimal expansion, we're going to let t sub n be this period, okay? And now I claim that since the limit of the q sub n's is 0, there exists some q sub capital N plus 1 such that q sub n plus 1 is equal to 0, and then we're going to have at least tau sub n plus 1 consecutive zeros in our decimal, because we can since the limit is 0, we can find it, as many consecutive zeros as we need. And so we can choose a rational number that has at least tau sub n plus 1. So I should say greater than or equal to tau sub n plus 1 consecutive zeros followed by a 1, because remember, all of these are non-zero numbers. Okay. And so now if I add this rational number to my sequence, so if I put this into my sequence q sub n sub k, which previously was going from k equals 1 to n, all of a sudden I'm going to break the tau periodicity of the partial sum. Okay, so now if I added this sum, if I take the summation from n plus 1 of q sub n sub k, must have a period strictly greater than tau sub n. Okay, so by iterating this process and by continually adding to this sequence, we can create a sequence of partial sums that has a period that are rational numbers with a periodic decimal expansion of period tau sub n that goes to infinity. Okay, and so this summation from k equals 1 to infinity of q sub n sub k must have an infinite period decimal expansion. And this is simply because if its period were finite, we could, since we've basically, by this algorithm, we've expanded the period by at least 1 every single time we've added a rational number to the sequence. So since we've done that infinitely many times, there's absolutely no finite period that this series could contain, and therefore we conclude it must have an infinite period decimal expansion, and thus this summation is in fact irrational. Okay, because every aperiodic decimal expansion number, or like infinite period decimal expansion number, is irrational. Okay, so this concludes the proof, because now we're just going to take the union of f sub n sub k's, and we're going to observe that the measure of the union of f sub n sub k's is precisely due to countable additivity. We have the sum of the measures of f sub n sub k's, and this is just the sum of the rational numbers that we've chosen here, and we've specifically chosen these rational numbers such that the sum converges to an irrational number. So this is irrational. And therefore, we've gotten that this measure must take an irrational value, which is a contradiction, because if we go back to the proof, to the starting claim here, we required that the measure takes only rational values. So this is the contradiction. It was quite amazing. We've basically started with a series of rational numbers that converges to 1, and then we said, well, we can choose a subsequence of those rational numbers such that, the partial sums have an expanding decimal period in base 2, and we can expand that period to infinity in a countable number of steps, such that we can choose a subsequence of the rational numbers with a series that converges to an irrational number. So we have a countable sum that converges to an irrational number, and that we can use that to draw the contradiction of our proof. So this was pretty tough to explain. I am trying to do better, and I appreciate your patience and understanding. If you're interested on measures and measure theory, I'm going to be doing a series on this a little bit later once I finish up chaos theory and partial differential equations. Have a nice night.